So today we're going to talk about a very important application of the Schrodinger equation, and that is a particle in a well. So I understand that before the midterm, which is on the 20th of November, you'll be able to cover the particle in a well problem, the tunneling problem, as well as some special guest lectures on superconductivity. So before I go into the discussion of a particle in a well, let me remind you of the time independent Schrodinger equation, which is minus h bar squared 2m d squared psi x. Now this is a function only of x because we're talking about the time independent Schrodinger equation, plus some potential energy ux psi x equals the total energy of the particle psi x. Alright, so this is the TISE. Now have we been able to solve this equation so far? We've been able to solve this equation for a very simple case. And what was the case? बताइए, हमने इस इक्वेशन को कभी सॉल्व किया? किस केस के लिए सॉल्व किया? For zero potential energy. That is, we assume that this is zero, this term disappears, and then this is a second order differential equation. We were able to solve this equation, and a particle which is in a potential free region is a free particle, and the solution to such a particle turned out to be a plane wave with of functional form kx. So the solution was proportional to EIKX. We cannot plot EIKX because this is a complex number, so we will have to plot the real part separately and the imaginary part separately. So this is the real part of EIKX, and we can also plot the imaginary part of EIKX, which is simply a phase displaced version of this wave function. Now this is the simplest case that we talked about, and we also realized that this is a synthetic case, an artificial scenario, that is a free particle that is in a potential free region, that is seeing no force whatsoever. Of course, there is no region in the universe where no forces really exist. There is the gravitational potential energy always, if we talk about the interstellar medium. But this is a hypothetical scenario. Let's talk about more realistic scenarios. And for realistic scenarios, we will have to assume some potential energy function. We'll have to assume what the form of this potential energy function looks like so that we are in a position to solve this equation. Let me give you a simple example. All of us are fond of photography, and modern cameras work. They have detectors called CCD cameras. CCD stands for, what does CCD stand for? Our digital cameras have CCD detectors. You've all heard the word CCD TV. What does CCD stand for? Sorry? Exactly, this is a charged coupled device. A charged coupled device. Now how does a CCD camera work? A CCD camera comprises a large number of pixels, and each pixel is in fact a semiconducting junction. And if I want to draw the picture of the CCD pixel, it will look as follows. There is an electrode, which is of course a metal electrode. It's called the gate. Beneath this metal gate is a layer of silicon dioxide. Further down there is N-type silicon, and even further down there is P-type silicon. And then you have to close the electrical circuit, so you make another connection. So this is a positive terminal, this is a negative terminal. Now when light shines on this pixel, because that's what a camera does, it is detecting incoming photons, and a CCD camera is sensitive enough to detect only a few photons. There are detectors available that can detect single photons. Now when a photon comes and strikes this structure, it liberates electrons. This is a process that we will study later. A photon comes in, electrons are liberated. Now there is a lone electron inside this structure. An electron has been ejected. Now the electron is not in vacuum, it's not in a metal, it's in a complicated structure which comprises junctions between silicon dioxide and N-type silicon, a junction between N-type silicon and P-type silicon. So this junction in fact creates a potential well. Now what does a potential well mean? A potential well means that if you have on one axis distance and you plot the potential energy on the other axis, then the potential energy is constant at some point over some range, and then it suddenly drops and makes a depression in the potential energy function. So this is what we call a well, कुआं. ये potential energy is no longer constant. The potential energy is constant over some range, then it depresses, that is the potential energy is lower in this region of X. It remains low and then goes back up again. This is an example of a well. So in this case a potential well is formed in this direction. So you have a well like this. Now this electron that has been ejected from a photon is seeing a potential energy function Ux which resembles a well. So if we have to find out the wave function of this electron inside the CCD pixel, we'll have to solve the Schrödinger equation, assuming that this is the functional form of the potential energy function. Now consider a polymer chain, a long molecule such as DNA. If an electron is injected onto the DNA, it's put onto the DNA, it is confined to exist along the length of the DNA for all times. So what is the wave function for such an electron that is confined to remain on a linear molecule? There are countless examples what one can think of in which one has to solve the Schrödinger equation for an electron inside a well. And this is something that we're going to study now. But before studying the confinement of an electron to a well, let me motivate you through an example in classical physics. And that example is very simple. Suppose you have a mass m that is attached to a fixed support through a spring. And this is your x-axis. The spring constant is k, the mass is m. Now the question that I would like to ask is whether this is a bound system or not. And I would like to ask what is the meaning of a bound system. Now what I would like you to do is to plot the potential energy of this system versus x. This system will have a certain potential energy. I would just like you to plot its potential energy versus x. शाबाश ठीक नेगेटिव एक्स भी तो हो सकता है This is quite simple. This is x equals 0, which is the mean position of this mass. As x goes up, as you displace this mass from its equilibrium position, its potential energy goes up, and the potential energy ux is given by half kx squared. This simple formula you would all remember from your mechanics class. So as x goes up, as you elongate the spring, the potential energy goes up. Then the mass comes back to its equilibrium position. You compress the spring, x decreases, but the potential energy goes up. So if you plot versus x, the potential energy ux, it looks like a parabola having this x squared dependence. So this is the potential energy function. So the potential energy goes on increasing as x keeps on increasing. Now the system will have some fixed energy. The energy of the system will be fixed. Suppose the energy is E. If E is the total energy of this mass, then this E comprises a kinetic component and a potential component. Suppose we fix the energy. That is, we take this mass, elongate it, and then we let it go. By elongation, we have fixed the total energy of this mass. And now the mass is oscillating between two extreme positions. And it is continuously juggling its energy between kinetic energy and potential energy. So the total energy of the system, suppose this is E. This is the total energy of the system, and this is the potential energy curve. Now what happens at x equals 0 is that all of its energy, the potential energy is 0, therefore all of this energy must be kinetic. As x goes up, for example, x reaches this point, a part of its energy is potential. This is the potential energy, and the remainder is its kinetic energy. So this is kinetic energy at x1. As you go up, you reach this point, all of its energy is potential energy, and the kinetic energy goes to 0. Likewise, you can draw these lines on the other side of this axis as well. So there is a constant interplay between kinetic energy and potential energy. At the extreme points, all the energy is potential and there is no kinetic energy. That's why the mass will come to a rest at the extreme point. This is something that you know very well. But if E is fixed, is it possible to reach this point beyond this extreme position? No, because this would imply a negative kinetic energy. This would imply a negative kinetic energy because this is the total potential energy U at x2, but the total energy is smaller than the potential energy, so the kinetic energy has to be negative. But this is nonsense. The kinetic energy cannot be negative. You all agree with me that this is nonsense. But not so in the quantum world, but here we're looking at a classical system. So in this classical system, this total energy and the potential energy curve intersect at 2 points. This is point B and this is point A. And these are turning points. So these are turning points, and when two turning points exist, the system is bound. We have a bound system, that is, the displacement cannot go beyond a certain point. When the mass reaches the point B, it reverses its direction, comes back to its equilibrium position and moves the other way. When it's moving the other way, it reaches position A, it cannot go beyond A. It reverses its direction, takes a U-turn, comes back to its equilibrium position and moves onwards. So the system is bound between the two extreme positions A and B. And this potential energy curve resembles a well. This is like a well. ये कुएं की तरह. So this is a classic an example from classic physics. Now let's move into the quantum world. Now in the quantum regime, suppose, let me motivate this by a physical example. Suppose you have two parallel plate capacitors and the capacitors are charged such that this is positively charged, this plate, and the other plate is negatively charged. This plate is positively charged and the other plate is negatively charged, and there is a certain separation between these plates, D, this is D, and this is a strange parallel plate capacitor because there is a hole inside this. There is a hole here and there is a hole here, there is a hole here and there is a hole here. Now suppose there is an electron. This is an electron. I am doing a bit of injustice because I am drawing the electron as a particle, but there is an electron in between the two parallel plate capacitors. So what will happen to the electron? The electron, we all know, is negatively charged. What will happen to the electron? The electron will be attracted to the positive sheet. So it will be attracted to the positive sheet, and what will happen when it passes through the hole? Will it keep on moving? Will it keep on moving? it will decelerate, because this electron has a certain kinetic energy. It will enter this region in between the two parallel plates and it will decelerate. So it will keep on moving, but its velocity will decrease. Eventually it will come to a halt and it will reverse its direction, because this is a positive plate. It will reverse its direction, gain kinetic energy in between the plates, because it's moving in the direction of the electric field. It will gain kinetic energy, move out of the hole, and will reach, traverse this region and go through the other parallel plate capacitor, and will be doomed to this perpetual motion inside this system. So the electron is now moving in between the two parallel plate capacitors, and if we would like to draw the potential energy of the electron in this system, what would it look like? Can you attempt at drawing the potential energy of the electron in this system? With respect to x, just make an intuitive guess of what the potential energy of this electron will look like. उसकी काइनेटिक एनर्जी है ना, वो पोटेंशियल एनर्जी को ओवरकम कर लेगा.
जैसे इतनी ज़्यादा अगर उसने वहाँ स्टार्ट किया था जहाँ पे भी हुआ है, तो इतना दूर कहाँ कैसे चला गया उसके अंदर कुछ नहीं बैठा.
चलो वहाँ से स्टार्ट कर लो, दरमियान से स्टार्ट कर लो, जा सकता है.
जब यहाँ इसकी इधर आएगी बिल्कुल यहाँ पूरी पोटेंशियल हो जाएगी, और जब यहाँ आएगी यहाँ जीरो हो जाएगी, वैसे ही बनेगा. मैंने
हाँ बना के देखो.
इस तरह नहीं होगा, यहाँ पे जाएगा,
इससे मिलता जुलता होगा. तब नहीं होगा ऐसे, तब ऐसे नहीं होगा. ये पॉजिटिव होना ज़रूरी है इस आर्ग्यूमेंट के लिए. So if I plot the potential energy, intuitively it will look something like this. It's constant in between in this region, and it goes up. Goes up like this, and then it goes up like this. Because in this region, when it enters this region, the kinetic energy has to overcome the potential energy, and that is why it will move a certain distance in this region and then reverse its direction. And the total energy of the electron could be something like this. So we have to define the total energy. So the total energy of the electron is given by this red line, and the orange line represents the potential energy curve. G. So in between these parallel plate capacitors, the potential energy is constant, the electric field is constant. Now this is a positively charged plate, this is a negatively charged plate. The electron wants to cling to the positive plate, but if it moves away from the positive plate, it is going against the electric field. The electric field is dictating it to remain near the positive plate. It's going against the electric field, which means that its potential energy is increasing, and it is able to overcome this potential energy only because there's a difference between the energy and the potential energy, and that difference is the kinetic energy. By virtue of its kinetic energy, it is able to overcome the potential energy barrier, and it comes to a halt. There's a turning point when the total energy equals the potential energy. That is where the kinetic energy goes to zero. So the electron comes to a halt and it reverses its direction. So it's going uphill here, and then it comes downhill. So this is an approximate form of the potential energy curve for this system. Now what happens if I reduce the separation between these plates?
So why isn't the potential energy zero between the plates?
Well, the potential energy is with respect to a certain reference, you can take this to be 0. It does not matter. It's some reference. Now what will happen if the separation between these plates is decreased? What will happen to the steepness of this curve? This curve will become steeper and steeper. So if the separation between these parallel plates is decreased, that is d decreases, this d also decreases, then this potential energy, this curve becomes steeper and steeper. Eventually, in the hypothetical scenario that this is an infinitesimal separation, this separation is extremely small, it's almost 0. The scenario that you get is the following. Now what we've done is we've decreased the separation between these plates, that is we have decreased this d and we have decreased this d such that d approaches 0. In such a case, the potential, this well becomes steeper and steeper, and these walls, they are inclined in this case, but as d decreases, the walls become steeper and steeper. Eventually you will have this situation in which these walls are so steep that there's a 90-degree angle here. And the potential energy goes to infinity. This means that this potential energy is so steep that an electron cannot penetrate this plate and enter the region between the two parallel plates, because really there is no region between the two parallel plates. So this is a limiting case that we will study today. And this limiting case means the following. In between the two plates, the two capacitors, in this region the potential energy is 0. Here the potential energy is 0. You can take any reference value for the potential energy, but it's easier to take 0. क्योंकि potential energy का कोई reference आपको चाहिए होता है. You can take a constant here as well, but the calculations are simpler if you take 0. And outside this region, the potential energy goes to infinity. Now whatever energy the electron has, suppose it has an energy E. Now in this region between 0 and L, the energy is greater than the potential energy. So the electron will have a certain kinetic energy. This will be the kinetic energy of the electron. However, this is a turning point, and this is a turning point, because beyond this turning point the potential energy is greater than the total energy, and kinetic energy cannot be negative. So this region is forbidden for the electron, and this region is forbidden for the electron. These are called classically forbidden regions. So this is one classically forbidden region, and this is another classically forbidden region. We have two classically forbidden regions, and what we have done in effect is we have trapped the electron inside this potential well. The electron is destined to remain inside this well for all time eternity. It cannot go outside the well, because this is a classically forbidden region, and so is this. The electron will always remain inside the well. Now in this situation, in real life, no potential is as sharp as this, but this is the simplest case that we can consider, because it allows us to solve the Schrödinger equation, and that is what we're going to do now. So motivated by this physical example, Let's solve the Schrodinger equation. And what does solving the Schrodinger equation mean? Solving the Schrodinger equation really means that we have to find the wave function. So we have to find the wave function of the electron inside this region. And what is the wave function of the electron in the classically forbidden regions? Could you estimate or guess what the wave function should be in the classically forbidden regions? Now what is the interpretation of the wave function? Probability density. Modulus squared of this gives you the probability density. What's the probability of finding the electron in the classically forbidden region? 0. So what's the wave function? 0. So the wave function is 0 in this region and the wave function is 0 in this forbidden region. What needs to be found is the wave function in the well. So let's find out the wave function inside the well. It's going to be a simple routine calculation. We have the Schrodinger equation, d squared psi dx squared. Now this is a function of position only, plus u now inside the well. What is the potential energy inside the well? 0. So this term is 0. We can also write this as d squared psi x plus dx squared plus 2m e h bar squared psi x equals 0. Now can you solve this equation for me? आपने डिफरेंशियल इक्वेशंस का कोर्स लिया हुआ ना, ये की है ना सॉल्व? तो क्या सोल्यूशन है इसका? So this is the solution of the wave function of the Schrödinger equation inside the well. Now we have two arbitrary constants A and B, and we have to find what these constants are. So there are certain properties that this wave function must satisfy. The first property that we've already studied is that the wave function must be normalized. Because only normalized wave functions make physical sense, because of the requirement that the probability of finding the particle somewhere has to be equal to 1. The other property is that psi is continuous. And why does the wave function have to be continuous? Suppose we have a wave function like this. Now here there is a discontinuity in the wave function. Now a discontinuity can only be achieved by having here a wave that has zero wavelength. So if you bring this right portion of the wave function towards the left portion, then the wavelength of this connecting wave drops. And when the wavelength goes down, lambda goes down, k goes up, the momentum goes up, and when you have a discontinuity, the momentum really goes to infinity. And when the momentum goes to infinity, the energy goes to infinity, and this is not allowed. So this is a simple hand waving argument that the wave function has to be continuous. The third requirement is that the first derivative of the wave function is continuous. Because if the first derivative of the wave function is not continuous, the second derivative of the wave function goes to infinity, and then you have an unrealizable, an unphysical situation. There is another requirement that the wave function can never go to infinity, because then you will have infinite probability, which does not make sense. So there are certain requirements in order to have legitimate wave functions. And we will use the second requirement here, that the wave function is continuous, in order to solve these coefficients A and B. Now let's suppose there are three regions. This is region number 1, this is region number 2, and this is region number 3. We know that the wave function in this region is 0, the wave function in this region is 0, and we know that the wave function in region 2 is given by this. Now can we find out the values of A and B? In between region 1 and 2, the wave function in region number 1 at x equals 0 is 0. The wave function in region 2 at x equals 0, that is the boundary between region 1 and 2, is given by this function, and you insert the value of x here, which is 0. So you get A plus B. But this wave function must match this wave function. So A plus B must equal 0, which means B must equal minus A. So this means that the wave function in region 2 is given by A 2m e h bar x minus e minus iota So we have eliminated b using the continuity of the wave function. Now there is an interface between region 2 and region 3 as well. We know that in the region 3 the wave function at x equals L must be equal to 0, because in region 3 the wave function is 0. But in the region 2 the wave function at x equals L is given by a e, let's write it in this form, exponent I 2m e square root h bar L minus e exponent minus iota 2m e h bar L. Now what is this expression equal to? This expression is simply equal to 2 iota sine of 2me But what must this be equal to? This must be equal to the wave function in region 3 at x equals L. So this must be equal to 0. So let's make a substitution. Let 2me square root over h, let's call this equal to k. Let's call this constant k. We give it a name k. So this expression becomes 2 iota a sine of kl equals 0. Now when is the left hand side equal to 0? Can we have a equals to 0? A equals 0 satisfies this equation, but if a were equal to 0, then the wave function in region 2 will be 0, which means that the particle does not exist. But we have assumed that a particle does exist. So a cannot be 0. So the only way in which this expression can be made equal to 0 is by imposing certain conditions on KL. And those conditions are that KL must equal n pi. Where n equals, n की क्या values possible है? 0 नहीं लेना, 1, 2, 3 and so on. So now we have a condition on k. K equals n pi over L. So now the wave function in region 2 is given by A यहां से हम लिख लेते हैं, ये वाली is given by A times 2 iota sine of kx, where k is constrained by this relationship. This is our wave function in region 2. The wave function in region 1 is the same as the wave function in region 3, and that is identically equal to 0. So now we have solved the Schrödinger equation in its completeness. However, there remains the task of finding this arbitrary constant A. We have to find this arbitrary constant A. Now how do we find the arbitrary constant? Look at the properties that the wave function must satisfy. Is there any property that we can use? The first one, the wave function has to be normalized, which means that the wave function complex conjugate into the wave function itself integrated over all of space from minus infinity to plus infinity must equal 1. But the wave function is 0 outside the well. So we can replace the minus infinity with a 0 and the plus infinity with an L and insert. What's the complex conjugate of this wave function? It's minus 2 iota A star sine of kx multiplied by the wave function itself 2 iota A sine of kx, and you have to integrate with respect to x, and this integral must equal 1, and you can solve this integral and find the value of A. And when you do this normalization, when you apply this normalization condition, you can find out the exact form of this wave function, and the exact form turns out to be, you can do this as a homework, turns out to be 2 over L sine of kx. Now let's move, we've done enough maths now. Let's move to the graphical interpretation of what we've done so far. Are there any questions up till so far? The first thing I would like to point out is the following. I've made a replacement 2me over h bar equals k. And k is just some constant. But what is the physical meaning of this k? Let's take the square of both sides. 2me h bar squared k squared. But what is h bar squared k squared? If k were the wave number, then h bar k is the, what is h bar k? It's the momentum according to the de Broglie condition, if k were the wave number. So if k were the wave number, then this expression is simply the momentum squared, and the energy we all know very well is p squared over 2m. That this is the kinetic energy of a particle which is in non-relativistic motion. This is the total energy as well as the kinetic energy of a particle in non-relativistic conditions. So we are indeed justifying in stating that this constant equals k, and k is nothing but the wave number, right? So this k is indeed the wave number, and the wavelength of the wave function of the matter wave will correspond to 2 pi over k. But now we know that k has been constrained. K has been constrained. There is a certain constraint on k. Remember, these are very illuminating results, and these will dawn a new world upon you. We have just confined the particle to a finite length between 0 and L, and what comes out as a result from solving the Schrödinger equation is that k cannot take any value its little heart desires. K can only take specific values, and its value is constrained by n pi over L. So k is now constrained by n pi over L. What does this mean? This means that 2 pi over lambda has to be equal to n pi over L. What does this mean? This means that lambda over 2 equals L over n. What does this mean? This means L equals n lambda over 2. Now does this relationship look familiar? Stationary waves, standing waves. ये वही रिलेशनशिप है जो आपने मैट्रिक, एफएससी, ओ लेवल, ए लेवल, फर्स्ट ईयर मैकेनिक्स में देखा होगा कि दिस इज द रिलेशनशिप फॉर अ स्टैंडिंग वेव. A standing wave that is confined to the length L. Its wavelength can only certain wavelengths are allowed. So now what we really have is the matter wave, or the wave function is in fact a standing wave inside the potential well. So if I redraw the potential well, for n equals 1, L equals lambda over 2. So this is the fundamental mode of the standing wave, and this could be represented, the wave function could be represented by this. There are only 2 nodes and 1 antinode, and the wave function is 0 outside in the classically forbidden region. So this is the wave function for n equals 1. It's just a standing wave with n equals 1. For n equals 2, L would equal lambda. Just look at this relationship. So the wave function for n equals 2 is the following. It's just a standing wave whose wavelength is such that one wavelength fits into the length of the well. This is the wave function for n equals 2. We can plot the wave function for n equals 3. It will have 3 wiggles, like this. And we can plot all the higher modes that are possible. So all of these are solutions of the Schrödinger wave equation, and these are all the legitimate solutions. You have the Schrödinger wave equation for an electron confined in a potential. The wave functions cannot take up any form. They are constrained to be standing waves, similar to standing waves, and depending upon the value of n, you can have different patterns. You can have the fundamental wave, you can have the first harmonic, you can have the second harmonic, and all of these are possible, but nothing else. So this n is called a quantum number. This n is given this innocuous name of a quantum number. Now what about the energy? What about the energy of this wave? All of these are solutions. So the electron can be in any one of these states or can have any one of these wave functions, but what about the energy? This wave function will have a certain energy. This wave function will have a certain energy. Can you tell me what the energy of these modes is? We have to use this relationship. See, so if we use this relationship, I've run out of blackboard. The energy is equal to h bar squared k squared over 2m, but k squared is quantized. Now we have quantization of the wave number, and we're checking whether we have quantization of the energy as well. K is given by n pi over L. So k squared is pi squared n squared over L squared. Let me recast this in a slightly more amenable form. We have n squared h bar squared pi squared over 2m L squared. So now the energy is depending upon n. The energy depends upon n. So the energy has now become quantized. The wave number is quantized, k is quantized. And energy is quantized. So I can put a small n here. This is exactly similar to the quantization of energy in the Bohr's model. And how has this energy become quantized? Where has this quantization come out from? This is a very interesting question that I would like you to ponder when you go home, if you have time, which you don't have. But just look at the beauty of the argument. We started with the Schrödinger equation. We imposed certain continuity requirements, and lo and behold, the wave number turns out to be quantized and the energy turns out to be quantized. So this is a general property of quantum systems, that whenever we confine something, whenever we confine a particle, it leads to quantization. That is, confinement leads to quantization. Confinement results in quantization. And that is why nanotechnology is so important, because you are making things smaller and smaller. You are confining the space over which electrons or other particles can exist. You get these quantum effects in the nano world. So now the energy is quantized, the wave number is quantized, and the energy is proportional to n squared. So if I plot the potential well here, and I plot a big well now, so the lowest energy state, n equals 1, corresponds to a wave of this kind. It's a standing wave of this kind, and the energy is E1. It is equal to h bar squared pi squared over 2ml squared. For n equals 2, I have the first harmonic, another standing wave. This is n equals 2, and the energy is 4 times the energy of E1, because it's an n squared factor. For n equals 3, I have this standing wave. This is n equals 3, and the energy of this wave function is 9 times E1. Therefore, the energies are not equally spaced, but the energies increase quadratically. And we can tell what the wave function is. The wave function of this particular mode is 2 over L sine of kx, with k is now given by 3 pi over L x. The wave function of this mode is 2 over L sine of 2 pi x over L, because k is now 2 pi over L. So there is an infinite number of possible solutions of the Schrödinger equation, and what you recognize is that the energy has now become quantized. And whenever a transition from one energy, this is one energy level, this is another energy level, this is a third energy level. So we can think of energy levels existing inside the potential well. And whenever a transition is made by electrons between energy levels, we get photons emitted, or we can absorb photons and make transitions between energy levels. So this is like an artificial atom. In an atom, the energy is quantized. We've learned that from the Bohr's model. Here we have gone deeper and used the Schrödinger equation to help and guide us that whenever we apply the Schrödinger equation to a particle confined to a certain region in space, the energy becomes quantized. And a few very interesting observations. The first observation, what is the lowest energy state? What is the lowest energy of the electron? What's the lowest energy? H bar squared pi squared over 2 ml squared. Now the question is, why isn't the lowest energy 0? In classical physics, we can have a mass attached to a spring, but the mass is stationary. You take it inside vacuum, there is no potential energy, the energy can be 0. If you cool a solid to 0 kelvins, which is the absolute 0, there should be no thermal motion of the electrons. But here we see that the minimum energy is not equal to 0. So this is a result of, this is a unique characteristic of quantum physics, that the minimum energy can never be equal to 0. And this energy is called the 0 point energy. The minimum energy can never be equal to 0. This is called the 0 point energy or vacuum fluctuations. Even if you have vacuum, that is, before the universe existed, there was vacuum. Even that vacuum had energy, and that energy resulted in the formation of the universe. So, the 0 of energy does not exist. Even at 0 kelvins, every electron, every atom, every ion will have some residual motion. And that residual motion is called the 0 point energy. Can you prove this statement by using the uncertainty principle? Can you give me a logical argument why the minimum energy cannot be 0? Anyone from the back? Anyone? आप बताइए. Exactly. Another way to look at this is, we know that delta P, delta X has to be equal to greater than H bar over 2. Now delta X is L. But if we confine or if we say that the electron has 0 energy, it means its energy is well known, which is 0. And when the energy is well known, the momentum is well known, which is 0. So this would become 0. But this is not possible because you have to satisfy the uncertainty principle. Therefore, the 0 point energy is a direct consequence of the uncertainty principle, because then you know both the position and the momentum of the electron, which is not possible. Now one last question before we break for the class, we have another 5 minutes, is talking about probability densities. Now suppose you have this wave function. The electron is in the n equals 2 state. This is the ground state for the electron, this is the excited state. Now remember, these are very important concepts. अब ये एक excited state है. Suppose the wave function is this particular wave function. Can you tell me what the probability density function will look like? This is the wave function. You can immediately tell me what the probability density function will look like. आप बताओ, इस रो से कोई बता सकता है? यहाँ पे से कोई कैसे निकालेंगे probability density function? वेव फंक्शन से कैसे निकालते हैं प्रोबेबिलिटी डेंसिटी? मॉड्यूलस का स्क्वायर ले लें, तो ये तो है ही रियल वेव फंक्शन, इट्स अ रियल वेव फंक्शन, इसका स्क्वायर होगा, स्क्वायर क्या हो जाएगा? साइन स्क्वायर्ड हो जाएगा. So this is the probability density for the second mode. ठीक है, ये probability density है, इसका स्क्वायर्ड है, यानी this will be equal to 2 over L sin squared 2 pi x over L, and this is what it will look like. So now if you perform a measurement on the position of the electron, you will measure the electron, the wave function will now collapse. This is your field, this is your matter wave, this is your wave function, all of them are the same thing. Your field will collapse into a particle and you will measure the electron to exist somewhere. देखो ये probability density है ना, और ये wave function है. अब वेव, जब हम कोई मेजरमेंट लेना चाहते हैं, हम वेव फंक्शन का मॉड्यूलस स्क्वायर लेते हैं, we get the probability density function. Now we perform a measurement and the question we would like to answer. So I give you the question, भाई साहब, I give you the question. Now the electron is in the excited state. Where does the electron exist? What you will do is you will take a measuring instrument and find the position of the electron. You will take a microscope, for example, okay, which works on the Compton principle. You will take a microscope, you perform the experiment and note down the position of the electron on your notebook. Then I give you an identical system. Dobara, identically prepared system. You perform the measurement again. You perform the measurement a large number of times. Sometimes you measure the electron to exist at this position, sometimes here, sometimes here, sometimes here, sometimes here, sometimes here. You perform the experiment a large number of times on identical systems, prepared again and again. ये नहीं आप करेंगे कि सिस्टम आपको दिया, आपने मेजर किया, फिर दोबारा उसी सिस्टम को मेजर किया, because the wave function has now collapsed. I have to give you another system which has an intact wave function, which has not yet collapsed. This is a very important thing. So you perform the experiment a large number of times, and if sufficient statistics have developed, you will get this frequency or this density. ठीक है, हिस्टोग्राम बनाएंगे तो इस तरह का लगेगा. और the key point is that you will never detect the electron to exist at the center of this well. You will never detect an electron existing at the walls. Of course that's reasonable because the wave function has to be continuous, but you get a very surprising result. First of all is that the probability density is not uniform over this well. The probability density is not uniform over this well. This is something very strange, extremely strange. That is, the probability density is not uniform over the length of the well. Classically it should be uniform, but now you have a non-uniform probability density. The third very strange result, the third extremely queer result is that there are certain points along the length where the probability density is 0. Here the probability density is 0. You will never detect the electron to exist here. The most probable position of the electron will in fact be at 1 over 3 of the length and 2 over 3 of the length. In this case, if you draw the probability density function, it will have 3 lobes. And the electron will never exist at this point, and the electron will never be detected at this point. The maximum probability of detecting the electron will be at these positions, this position, this position, this position. So now the probability density, these are called nodes, where you can never find the electron. Now the question with which I would like to end this class is a very important discussion when we study orbitals. If the electron cannot exist at this central point in n equals 2, how does an electron move from the left half of this well to the right half? Because if the electron were to move from the left half to the right half, because there's only one electron and there's a probability of detecting the electron here and a probability of detecting the electron here, there's one electron, it must move across this node. And when it moves across this node and you have a high speed camera, you should be able to detect the electron as being able to exist here. But how does an electron move across the node? So with this I would like to end today's discussion, and we'll meet on Wednesday. And think about this.